All right. All right. So apparently it's recording. I'm happy with that. All right. So today, well, this week we're going to do, like last week was properties of a single wave going somewhere through a medium. We talked about things like frequency and wavelength and amplitude and velocity, which is frequency times wavelength, and then also velocity as material properties. So we'll come back to that for the next lab. We're going to introduce velocity as a function of material properties and talk about how waves interact with each other. And you saw a little bit of this, right? So superposition is going to be very much a repeat of what you saw in the lab. I'm not going to spend a huge amount of time on it. There's not a big mathematical description. It's just adding amplitudes, and that's what you did in the lab. But we'll also talk about what you saw in the lab. All right, when you send two pulses, sometimes they add up and sometimes they cancel out. And so we're going to get into interference. And then we're going to say, well, what happens when waves of different frequencies meet? That's the first thing we're going to do is talk about beating. And then eventually we'll get to how musical instruments work. We'll talk about forming standing wave patterns where a wave interferes with its own reflection. And that causes a pattern to form in the medium where certain wavelengths are accentuated, they resonate, and other ones are not so much. They don't do as, they don't get canceled out. They just have some messy form instead of a resonant form. That's probably today. And then on Thursday, we'll keep going with standing waves and we'll talk about Doppler effect. If you've heard the nightly weather report and they talk about, their fancy Doppler radar, I'm going to tell you how that works. And we're going to do it in the sense of sound, which is slightly different than how it works for light. Mostly because light's nice. It doesn't have a medium. Sound has a medium. So, it'll be a little more complicated for sound, but at the end of the year, it'll make sense for light. All right. So this is where Zoom is going to be weird on me. So we're going to start with beating of waves. What happens when waves of different frequencies meet? And the reason I want to do that is because I can actually let you hear it. But the mathematical description, we have two waves. So here's the first one, which has one frequency. In this case, has angular frequency omega 1. And then so the counting frequency F is omega over 2 pi. And then we're going to add a second one that is slightly different. Right? It's just, in this case, it's a little bit faster, a little bit higher pitch. When we talked about pitches, when we talked about sound, we're talking about a pure tone with a constant frequency, not an addition of frequencies. So we're taking two pure tones and we're going to mix them. And what you get is this odd thing. And so what I want to point out is that at certain points, say, let's turn on the, can I turn on the, I want to turn on the pen. So let's say at this point, which is clearly kind of the maximum, then there's, I'm having to cheat this one a little bit. It adds up quite well. Is that there's a big, the point is at those points, you're adding two peaks or two troughs together. And so you get this amplified effect. Whereas here, where it's basically zero, you should be adding one peak and one trough. So in one instant, it's loud, it has a high amplitude, and in another instant, it's quiet, it has a softer amplitude, and it alternates loud, soft, that is a third tone. That is another tone you can hear. It's not perfect in the sense that your hearing is going to pick up something other than like a third pure tone. But in cases where you can measure it, it is multiple. You will pick up the additions of these two waves as basically a sum and a difference frequency. So this is where I kind of want to go and bring these up, and that's why I'm sharing this weirdly. So on the left, I want to play a concert A 1 octave below. All right, so this is 220 hertz. So if you've heard a band tune, they tune to 440. This is an octave below that. And you can hear that. Right. Now on the right, I'm going to start and play C sharp, which should be very nice and consonant. It should sound like a good chord. All right, so that's a couple of steps up. And there's the chord that you would hear. And you can go further. You can play a different tone up, but some notes, when they overlap like that, they sound good to you, and some, when they overlap, they sound bad. All right, we can play C sharp, and then we can play C, which is a little a semitone down, and it'll sound maybe melancholy or funeralist. And the closer you get to the original note, the worse it sounds. So we're going to stop that one for a minute. So actually, I want this one to be A again. So listen, this is 20 hertz difference. Sounds kind of a little weird. And what I'm going to do is back it down slowly. It gets worse. It gets kind of an ominous feeling. Now you can hear a distinct Now they're just 2 hertz apart, and you can hear a clock ticking twice a second. And there's nothing fancy about this. Is I could pick different tones if I wanted to. All right, so just different choices here. And that's the beat frequency you hear. So when a band tunes their instruments, that's what they're supposed to be listening for, is that beat frequency. I didn't know that when I played, and I was always like half a step out of tune, so it sounded like a chord and it was bad. But that's what they're listening for, is that beat frequency, and then they adjust one way or the other and try to figure out if it's right. Now I can go down in frequency and you get the same beat. All right, that's the important. All that matters is the difference between the two. All right, you're not going to get like a negative frequency. It's just the absolute value of the difference between them. So what matters here is that the beat frequency is F2 minus F1. Take the absolute value. So, I mean, that can come in basically when we're talking about other things, like when we're talking about musical instruments that are tuned. We could give, in a past exam, we did this. We said, you play your instrument, you play a flute or a clarinet or a saxophone, whatever it is. You play a tuba, let's say. Whatever it is, you play a note expecting to play a different note, and you're comparing it to your, like a tuning fork, and you hear a particular beat frequency, and you can hear yourself, and you're flat. What frequency are you playing? Which means you go through and say, well, I know my beat frequency because I can hear that. I can count. And I know one of them, I can figure out the other one. And then we can go from there and say, well, if you have this particular frequency, how long is your instrument? And we'll get into how to do that. Anyway. So generally, every other time we're going to talk about superposition, we're going to talk about adding waves that are equal in frequency. In this case, the drawing we have is just pulses. Anything we talk about there also applies to waves of different frequency, but it's complex. And so we kind of try to keep them separate. But in the lab, we talked about sending individual pulses. And just as an aside, what I want to say is the reason we talked about the wave equation for a nice, simple, sinusoidal wave is that, and you can ask the math people here, since we're in the math building, there is a property of waves, a property of any set of functions that you can build them out of sine waves or cosine waves. And the trick is getting the right summation of them to cancel in the right places and not cancel in the others. And that's why we call it superposition, is that's kind of what we're doing. We're taking a superposition of different waves. So when we're adding pulses like this, it works exactly the same as if we're adding entire sine waves, because in effect we are. So if you're interested about this, the thing you would look up is Fourier transforms. That's what you want to know about. And it mostly comes up in everyone else's life when they're playing with computers and music, or computers and sound or something. But anyway, what you saw in the lab, we're just going to claim is essentially going to happen for all waves, even though you only saw it for pulses. When you have waves meet and they are meeting what we call in phase, which means their crests line up and their troughs line up. Their amplitudes when they meet have the same sign. So in this case, both upwards. Then they add up. And the waves don't interact with each other. They pass right through each other. In the lab, you could have seen this send a big wave and a little wave. And the result after the addition would have been a little wave and a big wave. And it would have looked like that. So you could have tried this. Now, the other proof in the lab was to go ahead and do the next step, is to talk about what happens when you send waves with different amplitudes, one up and one down. So in terms of adding two sine waves, generally what happens, and you can see the dotted lines in this graph, the crests line up, and so you add the amplitudes, or the troughs line up, and you add the amplitude. And basically, one wave is a copy of the other one, up to this factor of the phase. So if the phase looks like 0 or 2 pi or 4 pi, it's in phase. They're going to line the crests and troughs up, and they're going to add up constructively. So this is what we call constructive interference. Let me pause there for a minute and figure out what got in my eye and ask if you have questions. Okay, good. All right, so sometimes, you can send a pulse that has sinusoidal shape in it. And, when that pulse meets, it's going to basically, this is saying we have a wave over here, that looks like that, and then a wave over here that looks like that. And when they meet, when they partially overlap, only the parts that overlap are adding up. The other parts are unaffected. But eventually they come together and they overlap, and you get effectively just an addition of the amplitudes. So if this were two sound waves, the effect you would hear is that this would be a louder sound. If it were light waves, it would just be more intense light. Let's see what else is there. The effect you saw in the lab, when the two pulses met, the amplitude increased, which meant basically had the energy from both waves in the same spot. And that was enough to move the plastic cups when either wave alone couldn't have done that. So when they are out of phase, when they have one with a positive amplitude and one with a negative amplitude, one up and one down, then the energy is still there, right? Because the energy is proportional to the amplitude squared. And so no matter what we call the sign of the amplitude here, pretending the amplitude is a vector and has positive or negative, up and down, amplitude squared is positive. So the energy is always going to be positive. The energy is still there. And in this medium, you still have the effects of, right? You see it at an instant, it is stationary, but it still has velocity up and down on the individual coils. So they're going to keep moving eventually. Right? So just as you just have a bunch of forces that are acting together from each wave, and they're going to result in velocities along the coil transverse to it. And so at the moment, there's no amplitude, but the energy is still there, and it shows up later. And this is the proof that the waves don't interact with each other, right? Because the wave that was on the left is now on the right, and the wave that was on the right is now on the left. They pass through each other and don't interact with it. They don't bounce. All right, so I don't know what these demos are exactly. Let's play them and see. Well, let's try to. What? Thank you, PowerPoint. All right, let's not even bother with that. Y'all can play it when you get to the notes and figure it out, and I'll try to figure it out for Thursday. But effectively, the demos that you saw in the lab is what you needed to see out of this. So in this case, this is what the destructive interference looks like for waves that are out of phase. Here, nope, go the other way. Give me my pen back. Here, the phase is something like pi or 3 pi or 5 pi. Right? And the phase being pi means that at the beginning, at some beginning point, I have minus the amplitude, and here I have plus the amplitude. So they start out of phase. They start with completely different values. Or they start with values that are pi apart. This distance here is pi. And that's what you see here is this distance is pi. So when they do that, you have the troughs line up with crests in the other way. And so you have plus amplitude and minus amplitude. And you add those, you get 0. So you get destructive interference. So in terms of sound, this would be a very quiet spot. In terms of light, it would be the absence of it. You would see a shadow, a darkness. And in terms of the lab that you did, you sent waves that could knock over cups by themselves, but when they met in the middle, the amplitude was 0 and they were no longer able to interact with cups. And so it left a pair of cups standing. So this is destructive interference. So primarily I'm going through this carefully so that the underlying math makes sense, so that when we talk about other problems, we can deal with it. So waves combined, when they overlap, you have destructive interference. If they partially overlap, you only get partial interference, and the remaining part doesn't overlap, stays just fine. So yeah. So you can have an effect that is in between, where if the phase difference is any other thing, don't worry about writing this down. This is unimportant. If you have any other wave difference in phase, and this is where that difference in frequency comes in, is you could hear, it wasn't, when you heard the beating, you didn't hear clicks of on and off. You heard, it ramped up in amplitude and back down. You can have intermediate additions where it's not really constructive, not really destructive, until you get this ugly wave equation form where you're adding them. But it looks something like the picture on the right. Is sometimes you're adding crests and troughs, but you're not quite in the right spot, so you get something left over. So the phase difference is what matters in whether you have constructive or destructive interference. And the phase difference is often a property of the geometry of the problem. So when we give you problems where you have basically sound from two sources, finding that phase difference is going to be the issue. We'll say it usually in terms of the physical distances between things. Right. Ignore that. All right, so I want to do a practice problem like we did in the lab, because I've seen this sort of thing on the exam. Is basically, here are two pulses. Can you come up with, or given that they're moving at some set of speeds, can you deduce the shape of the wave at times in the future? Right, so two waves, right now they look like that, but they are going to overlap. So a little bit in the future, what positions are they at, and then what is the addition of them? I'm going to pause for a minute, and I'm going to let y'all think on that, and we'll come back and we'll go over it. Okay. So what we have, all right, each wave is moving at 2 centimeters a second. And here is our x equals 0 spot. And so we want to know what it's going to look like half a second later. So the distance it moves is just velocity times time. 2 centimeters per second times 0.5 seconds is 1 centimeter. All right, so each of these waves are going to move 1 centimeter, one to the left, one to the right. So let's get some different colors here. So this wave is going to look basically like that in blue. And then we'll get green in here for this one. So that one just shifted one square over. Then the other one down here is going to shift one square over to the left, which means it goes from there and goes there, and then it goes up like this, and then it continues on like that. So now at this point in red, well, let's see, we have that it's 1 centimeter in amplitude in the blue wave and minus 3 centimeters in amplitude in the green wave. And that means 1 plus minus 3 is minus 2 centimeters. This wave should sit there. Right. And then you're going to do the same thing for other grid points. This part should be up here. And this part should be down here. So this wave should look vaguely like that, which kind of makes it look ugly, but the gist of it is at this point we're asking about, we have the solution. So that's the shifted wave, and then we get that it's minus 2 centimeters. Does that make sense to people? So that's hopefully what you've been doing in the lab, and there'll probably be problems like that on the homework and maybe one on the exam. So these slides use slightly different terminology here for sound. Right, we talked about, if you remember, we talked about sound waves. If we're going to plot the wave on a graph, we're going to plot the sound, the local pressure versus time, or the local pressure versus position. So these graphs here are pressure versus time. Right? And so what that looks like is really the wave spreads out, and you have areas that are compressed, marked with C, and areas that are rarefacted, marked with R, where the air pressure is higher or lower. So this is why it uses this condensation and rarefaction. What it means is higher pressure, lower pressure, or crest and trough. So the point of this is that in these diagrams like this, the condensation points are a wavelength apart, and the rarefaction points are a wavelength apart. Right? The high pressure areas are a wavelength, and the low pressure areas are a wavelength. So if they're in phase, then at a point where they meet will be constructive interference. And that's true wherever we happen to look. We can look at some other point. If they meet and they overlap, they're in phase, it's constructive, which means there's probably going to be a lot of places where it's constructive in here. Whereas if they overlap and there's a spot where, notice one other thing, these are the waves traveling the same distance, 3 meters here, 3 meters there. If they overlap and are out of phase, then it's destructive interference. Right here, we see basically one compression and one rarefaction. So they overlap out of phase and they cancel out. And so note that this is 3 meters and this is 3.5 meters. The wavelength here seems to be 1, 2. Ooh, the drawing is weird. That's what it is. The drawing is weird. 1, 2, 3. 1, 2, 3.5. Let me erase some of these so it's not. Yeah. You can look, there are basically 6 lines on this drawing and 7 lines on that drawing. So the wavelength is a meter in this picture. And you can see that one of them travels half a meter extra, and so it gets out of phase. This is assuming that these sound sources are playing in phase themselves. And that's the only case we're going to consider. We're not going to go and say, well, what if they're playing out of phase by some amount? So there's a place where this is important. Who has used like noise canceling headphones? So the way they work in general, the nice ones that have circuitry in them, they're a microphone. It picks up the ambient sound. There's a bunch of different frequencies, but it's just a wave. It's just a complex wave. It's a bunch of sines and cosines. And it has a little speaker inside which inverts the signal and plays it back, so that at the point of the speaker, there's the original wave and then a copy that's upside down. And so they cancel out. They don't cancel out perfectly because, you know, sound's coming from all around you and then from this little speaker, but it cuts it down a whole lot. It cuts it down to just a murmur. And so it kind of, you know, works out. Now, other sorts, you're just getting a lot of insulation. They're just like earplugs, effectively. But the nice ones, that's what's going on. They're playing a little. If you're in a car, and the car has, you know, is trying to deaden the road noise, they try to do this. They try to play the road noise backwards. Not always a great effect because it's a bigger area, but some cars do that. All right, so the gist is, if we have two wave sources, now this is one where I'm going to try to, let's see, I don't have them up now. Oh, what in the world? Oh. Go away. No, actually, that's not what we want. Oh wait, this is edge. That's the weird thing. All right. So I'm a little addle brain. Give me a moment here. I should have left that. I just did this, you know. So if I play this one tone, right? Now there are multiple speakers in the room, I think. Or is it just coming from this? But if you were to walk around the room, you would hear places where it is distinctly louder, distinctly quieter. We'll try to do this maybe for the next lab, is set up two obvious sources. But to just, if you've ever been in a house with a sound system and it's been poorly tuned, that's what's going on. Is they've not adjusted where you're trying to sit. But the gist of it is you have two sources. So the sources are in phase. If we pick a point, there's some set of distances to it. Say this distance here is, so let's say the wavelength is 1 meter, and then this is going to be 2.5 meters. And then this one is going to be, nope, that one, sorry, 2.5 meters. That was a poor one to pick, but that's okay. The point of this is, if the path difference is a multiple of the wavelength, then it's constructive interference. A multiple of the wavelength means that the phase difference is a multiple of 2 pi. If it's odd, all right, if you have a point that is here and it is an odd half integer number, like 1/2, 1.5, 2.5, then the phase difference is going to be pi, 3 pi, 5 pi, something like that. It's going to be an odd multiple of pi. And that's going to lead to destructive interference. There is a formula for this. I am going to get to the formula. All right, if the waves are exactly the same, the path difference represents the phase difference. And so you could have any sort of constructive or destructive, but identifying whether it's constructive or destructive is based on the path difference being either an integer number of wavelengths or destructively an integer plus 1/2 number of wavelengths. So this is one of those things where in problems you're going to work with it, you're going to have to determine whether you're looking for a loud sound is constructive interference or a quiet sound is destructive interference. And then you're going to have to deduce what the path lengths are. All right, so I'm going to go through and work an example that shows what we intend from this. All right, we have 2 speakers. They're emitting a constant tone. And speaker A is to the left of B, and they are playing a wavelength that's 1/2 meter. So we want to know where, and now there's no geometry in this. We're told the explicit distances between between the observer and the speakers. Right. So the observer goes around to these locations and checks, is it interfering destructively or constructively or in between? So the point of this is find out what D2 minus D1 is for each of these. And then you go and say, well, that number that you got, what is it in terms of the wavelength? So for the first one, we have 3 meters and 2.15. So the difference is, 0.85 meters. Then for the second one, we have 3 3/4 and 2.5. So we have 1 and 1/4 meters. So for the third one, we have 2.5 and 1. So delta here is 1.5 meters. And then for the third one, we have something weird. It's 3, 2, so delta is 2.4. All right, so now in terms of the wavelength, right, is we're going to basically divide. In here is our wavelength, our path difference divided by the wavelength, our perspective in, or something, if it's constructive, it's this. If it's destructive, it's something else. But we can go through and look at these. So for the first one, in here is going to be 0.85 divided by 0.5, and that's some ugly number. It's not going to be exactly a wavelength or a wavelength and a half. But here for B, N is going to be, well, we have 2 1/4. So, so we have, 2.5, 2.5. And then for C, N is going to be 3 because it's 3 times 0.5. So N here is the number you multiply the wavelength by to get the path difference. And then D here is the ugly. All right, so I'm going to come out even. So N is 3 is constructive, so it's not C, it's not D, and it's not A because they're weird. B is the one you want. So to be clear, what we did is We found the path difference first. That was this part. And then we figured out what that represented in units of the wavelength. And then we figured out which one gave us an odd number of half wavelengths, and ended up being B. Does that make sense to people thus far? Right. So this is just a question. Where's the best place to sit when you have two speakers? There's kind of an obvious answer, right? If you wear earphones, you have two speakers. You don't put one on one ear and then like one across the room. You put them basically equidistant. But the gist is, if we have two speakers, right? So say this distance is 5 meters, then you might want to be 2.5 meters if you're right between them. Even that's not saying anything about the wavelength, right? Because the speakers could be playing any tone. So you want to sit basically equidistant from them. And that's true. You could sit down here. And then so you just want these distances to be the same. As long as you're on basically a line that runs perpendicular to the line between speakers and goes through the midpoint, you're okay. All right. And this is the one I want to go through that's the sort of complex one. All right, so we have two loudspeakers. They're separated by a certain distance, 3.2 meters, and you are directly in front of one speaker, 2.4 meters away, with this nice geometry that's 90 degrees. So they're both playing the same tone, and they're both, the speed of sound's the same everywhere in this. So the point of this is what we've got here is the frequency and the speed. So we need to find the wavelength, because everything we defined here is in terms of the wavelength. But the point is to figure out whether we are at a point where we hear loud or no sound. So problems like this, what we want to do is find the path that the sound takes, find the distances for them, and then find the wavelength and compare the path difference to the wavelength. All right, so one we're given, sound goes from B directly to us, it's 2.4 meters. The other one we have to calculate, goes from A what did you do? It goes from A to C along that line. So we need to figure that out. But what I've just drawn is a right triangle. So we can look at this. And you just throw this in Pythagorean theorem. That makes sense. But this, if you remember your trig, this is a 3 and a 4. They're 3 times 0.8, 4 times 0.8. So this should be 5 times 0.8, which is 4 meters. Please check with the Pythagorean theorem, make sure that makes sense. So the other bit that we have is trying to find the wavelength from V is F lambda. Lambda is V over F is 343 meters a second over 214 hertz. Hertz being per second. I did bring a calculator this week. I'm almost certain this is 0.8. Or no, 1 point something, 1.2 or anyway, don't talk, just calculate. 1.6. So our wavelength is 1.6 meters. So now in terms of the wave that is sitting here, the path from A to C is really 2.5 wavelengths. And the path from B to C is really 1.5 wavelengths, 1.5. So the path difference here, we have 4 and 2.4. The difference is 4 meters minus 2.4 meters. That is 1.6 meters is 1 wavelength. And that's what we get from looking there. 2.5 minus 1.5 is 1. So they're 1 wavelength different. That means N is 1. It's an integer. That means it's a loud sound. So I'm going to pause there. Does everyone follow what I did? I had to find the wavelength in the problem, and I had to find the 2 paths, the 4 meters and the 2.4 meters, and then the path difference, which is 1.6 meters. And then I compared the wavelength to that path difference. And if it's a multiple, an integer multiple, it's loud. If there's an extra half wavelength, then it's quiet. So any questions thus far? Does that make sense? Good. So I believe the rest of this just actually works through the math appropriately. They did Pythagorean theorem to get that missing side was 4 meters minus, so the path difference. So this is on this side. This is AC and this is BC. So those two differences is 1.6 meters. The wavelength is 1.6 meters. Therefore, it's an integer difference. So in the homework, there will certainly be a couple of problems like that where you have some geometry and you have to figure out what the path lengths are. And that just means doing, these problems are all going to look like finding sides of a right triangle for that part. Now, we're not going to trick you with anything there. I did throw some weird stuff at the high school kids, but not you guys. All right. I'm on time. I'm going to go another 10 minutes or so, maybe 15. I do want to eventually show examples of some stuff on Thursday, hopefully. So we have waves, and you saw in the lab that they reflected. And if there's a point that is fixed for the wave, or if there's a point in the medium that cannot move, it's fixed, right? In terms of your springs, they were clamped to the table. They could not leave the clamp. Then that point must always have 0 amplitude. And so when waves come in those cases, what goes on in the appearance of, it kind of looks like a mirror image, right? So on the right, we have a mirror image and it's flipped over. And so reflections look like we're going to add a real wave and a mirror wave. And we know which way the wave looks because we know that the amplitude is either 0 or it's big based on how it reflects. So when we reflect, we're going to treat it like this mirror wave passes through and the real wave passes through. And so what we end up with is that the wave flips over. The pulse that we send flips back. Now, the thing I didn't have y'all do in the lab was send 2 pulses so that they were both in the same direction at the same time, because that would have showed you one flips and then the next flips, and you do a chain of them, 3, 4, 5. Eventually, if you just shake with a sine wave, all of the little pulses are going to also flip. So what happens is eventually we have this wave, it's going to meet itself. It's going to, if we have a long wave like this, and then a wave coming back, they're going to meet each other. They're going to interfere with each other in some way. So for most frequencies, it just makes a mess. You just see the medium shake. But certain frequencies, when it reflects, it will meet itself in phase. And so it resonates. It creates a larger amplitude. It creates what's called a standing wave. It'll basically, as the wave propagates, it's always meeting itself and constructively interfering. So it resonates. Let's see if this will play.
Standing waves are a result of reflection and interference. As I send a single pulse down to this fixed end, you can see that it reflects upside down on itself. If I send a rhythmic pulse, it reflects on itself. This is the fundamental mode. Sending the pulse at twice the frequency results in the second harmonic.
So notice that there's a point in the middle of the wave that doesn't seem to move much. Now there's 2
I get
points.
the third harmonic.
All right, that's enough. So we're going to start with stringed instruments because they look kind of like that. So anything where both ends are fixed. So you have a medium and the ends of the medium are fixed. They cannot move. But the middle can move, right? So you think a guitar string or a piano string. So what's going to happen is as you drive, right, you're going to have different cases where you have different resonant, different standing waves. In this drawing that we have here, we've labeled what are called the harmonics, the waves that can fit, that can resonate with the string. And so in the first one, what we have here is that L, the length here is going to be this distance. And so L here is lambda over 2. All right. And basically you see half a wave there, and it oscillates in the middle and it's fixed on the 2 ends. So the 2 ends stay 0. And in the second harmonic, then we have that the wavelength is equal to the length, and you can see a wave in this. That is one cycle of the wave, and it will oscillate back and forth between amplitude up and down in one part and down and up in the other. So it'll vibrate, but there'll always be this extra point where the amplitude is always 0. Right. And then in the third case, we have L is 3 lambda over 2. And that makes sense because we'll have this distance will be lambda. And then this extra distance will be half lambda. And so we'll have 2 points here that are basically 0 amplitude all the time. So points that are 0 amplitude are called nodes. And then the points where you have large amplitudes are antinodes. I don't know why they're called this. That's just the terminology. So the point of going through this is we can deduce what wavelengths and what frequencies for a given string will result in resonance. Basically, we'll know how to tune a guitar or a piano. So remember out of this that the velocity of the wave is this function of the tension divided by the mass per unit length, right? So that may come up in problems that you see as well. But it's also just the frequency times wavelength. And so, all right, we identify the nodes and we have a formula for what frequency will result in. Don't worry about writing this down at the moment. We're going to skip ahead. All right, the frequencies depend on the velocity in the string, which depends on the tension. And the wavelength is just a function of, as we identified, it's just the length and which harmonic we're in. So this is the one I want you to remember how to work with. This and lambda is 2L over N. So for a string that's fixed at both ends, like a guitar string, a piano string, things like that, anything where the two ends are fixed, the standing wave that forms can have effectively what we notice here is, let's look at this and just put n equals 1 in. The lowest possible frequency is just V over 2L. And V is a function of the tension in the string. But then every other one, Fn, is just n times F1. So you get a fundamental frequency. The first harmonic is the one that you tune for. But then you also get a second, a third, a fourth, and so on, that represents all the other possible waves that could fit on the string. And now what you'll also notice is that the first one has this huge amplitude. All of the energy is in this 1/2 of a wavelength. The second one is basically split. Half is in the first half, half is in the second half. So the left and right. And the third one is split. Each one has about the third the amplitude. And so general, the higher the frequency, the shorter the wavelength, the lower the amplitude is that will fit on this. All right, so, if you're tuning a guitar or if you're playing a guitar, right, the strings all have a natural frequency. They're the bottom note that you play. But if you want to change a note, you don't have to do something like drive it extra hard to cause it to resonate at a higher frequency. You just have to change the length of the string. And that, on a guitar, you do that by switching frets. On a piano, you change which string you're using. On a violin, you put your finger at the right point. So the natural frequency is just this F1. It's the fundamental frequency that you get. Right. So we're going to try to envision this and talk about what's going on a string. We have a string, it's 120 centimeters long. We know the mass of the string, and it's going to be some wave where n equals 3, and the frequency is going to be 180 hertz. So we can sketch that. Here's one fixed point. There's the other fixed point. This is 120 centimeters. Now, n equals 3 means there's 3 half wavelengths. So we'd put in 1, 2, 3. And then we'll put in a different color the other 2. All right. So from this, we can identify the wavelength directly. It's that. So it's 120. We're dividing it into 3 chunks. It's 40. So lambda is 80 centimeters. Now it's asking what is the tension in the string? Well, the tension is related to the mass per unit length and the velocity. The velocity we can deduce because now we have the frequency and the wavelength. So V is F lambda is 180 hertz times 80 centimeters per second. So 14,400, and we're going to convert to meters. 144 meters a second. Now we have the velocity and we have the mass per unit length. Mu is m over L is 0.004 kilograms per 1.2 meters. All right. And so now we can find the tension, basically reversing our formula for V is square root F tension over mu. So F tension, we're going to square both sides, and then we're going to multiply both sides by mu. So, we'll find out what these numbers are. 0.004 divided by 1.2. This is 3.3 times 10 to the minus 3 kilograms per meter. On the other side, I'm going to multiply by 144 squared. We get about 69.1 newtons. Again, the numbers aren't strictly important. The point is, how do you see a problem and identify what you got to do? If we're talking about a guitar string, you're probably looking at standing waves. And so that means you want the velocity from the material properties, or it's given to you, and you want the wavelength, identifying it from the sketch, or identifying it from the fact that n equals 3 and the string is 120 centimeters. You can work out that it's 3/2 of a wavelength on string, so you can work out what one wavelength is. So let me pause there. Do y'all have any questions? Does that make sense to people thus far? All right, we're going to practice some more of this on Thursday, obviously. Oh, okay. So this is a question, again, this is a question envisioning the wave. So if we draw a wave here, so it's asking from the fixed end to the nearest antinode. So let's put in 2 fixed ends. Let's put in an arbitrary wave. That is n equals 4. So in a different color, we'll put in the opposite wave and identify the 3 nodes that are there. So the nearest antinode, say to this one, has to be there. That is a quarter of the wave. Basically, to the first node is a half wavelength, and then you're going only half that distance with the quarter. Can everyone see that? Does that make sense? All right, so you can have the same sort of behavior in longitudinal patterns. It doesn't have to be transverse. And the point I bring this up is so that we can describe sound and describe how standing waves form in pipes. So you understand how the winds and brass instruments work. What time is it? Let's stop there. We'll go into pipes later. All right. So before I let y'all go, any questions about anything? If you have homework questions, stick around. I'll help with them. Otherwise, I will see y'all on Thursday. Also, yeah, if you have the lab from yesterday, let me have it so I can get you very in.